All right. Good morning, everyone. Welcome to the IvS seminar. The seminar is today given by Soetkin. She's a PhD, as you know, with us, and she's a very, very, very local person, right? So you did your bachelor at KU Leuven, master's at KU Leuven, although you decided to go for a year or a bit less abroad, and now she's again back and doing a PhD with us, which is great. As you guys can see on the slides, the talk is going to be in English, not in Japanese, luckily for us. And Soetkin is going to talk about massive stars with black hole companions today. The floor is yours.
Okay. Thank you, Andrew. Today I will be talking a little bit about looking for black holes around massive stars. So let's start with a very brief introduction to massive stars themselves. So massive stars are born with masses higher than 8 times the mass of the Sun, and they have OB spectral types. If we're going to position them in the Hertzsprung-Russell diagram, where you have the effective temperature on the x-axis going increasing towards the left, and the luminosity increasing upwards, then we find our Sun here somewhere around 1 solar luminosity and almost 6,000 Kelvin. And our massive stars are up there in the main sequence, just very hot, very blue. Now, after a while, yes, these stars will start evolving. And during their evolution, these massive stars, some may even lose over 25% of their mass during their lives. So they really enrich the universe and their surroundings with a lot of chemical elements. Also, they have very powerful ionizing radiation. So they really impact their surroundings strongly, for example, planet formation, other star formation. So they're quite important for that. And at the end of their lives, they will go a violent supernova, leaving behind a black hole or a neutron star. At least that's what generally thought. But in reality, we're not exactly sure if black holes are also forming with a supernova, right? Maybe some theories might suggest that we just have a direct collapse, so no mass loss, no supernova. And this leads us to unknown black hole formation physics. So it's not only whether they lose mass or not, whether they go supernovae, but I think even more importantly for binary evolution itself is whether they receive a kick or not. Because if you receive a strong kick, you might disrupt your binary system and you're left with 2 stars flying away from each other, well, or a black hole and a star flying away from each other. And as it turns out, most massive stars are actually found in binaries, so these kicks and this mass loss will be important for practically all massive stars. So, yeah, almost all are in binaries, so let's take a look at one example of how we believe that a massive main sequence binary can evolve towards a gravitational wave merger. One example, there are more, but I'll walk you through it. So we start off with 2 main sequence massive stars, yeah? And after a while, the primary, the most massive star, will start evolving, it will expand, it will fill its rush loop, and initiate mass transfer onto the companion. What is left is a stripped star for this primary, which will eventually, well, as I said, may or may not go supernova, but we end up with our first black hole. Yeah? We end up with a black hole plus a main sequence star. Now, after a while, this remaining main sequence star, the secondary, will also start evolving, start transferring mass onto the black hole. We get an X-ray binary. And this phase is, in this case, followed by a common envelope, after which we have a stripped star when the common envelope is ejected. This will, again, go supernova, or maybe not, but we end up with our second black hole. Yeah, so we have our double black hole plus black hole binary, which then eventually will merge. Now, in this diagram, there is a lot going on, a lot of mass transfer, supernovas, but there are 3 phases which are long-lived. This is the double main sequence phase, the phase where we have a black hole plus a main sequence star, and where we have our double black hole. And observationally, we have quite a lot of evidence for the first thing here, which is the double main sequence binary, and thanks to the gravitational wave, why we cannot directly observe our double black hole binaries, we can infer them, or we can practically see them. And so we know we have these gravitational waves. So we have a lot of, we know that these double black hole binaries, they exist. Now, this phase, the other long-lived phase, the OB plus black hole phase, has been predicted to be quite abundant, or to be present, but we are lacking a lot of observations. So if you look at predictions, when we assume that there is a direct collapse and that there is no kick, then 3% of all OB stars in binaries approximately should have a black hole component, which would lead, in our Milky Way alone, to over 10s within 3 parsec. Currently, there is like 2 references that I list here. One of them is in the Large Magellanic Cloud, so we can't even count it for the statistics. So we're really lacking some observations. And since we have observed these double black hole binaries, well, unless they all form dynamically, meaning that 2 black holes encountered each other and then formed a black hole, somehow there must be an intermediate phase where we have a black hole plus a main sequence star. So they must be there. So why are we not finding them? What has been done so far to actually find them? This is a slide with a lot of titles. You don't have to read them all. It's just to give you an overview of some of the reported black holes. Most of them are quite recent, as you can see, all in the 2020s, and then one in 2014. But these were still reports in the literature. Now, there has been a lot of follow-up on some of them, and we can exclude almost half of them, just by challenging them, finding different explanations for them. So they're not black holes. On top of that, I'm now going to exclude all the black holes around low-mass stars, and I'm going to only leave out the ones around massive stars, which is really not a lot. So we have our 2 practically confirmed ones, one in the Large Magellanic Cloud, right, so not Milky Way, and then we have maybe a couple more candidates here. But so there are really very few still accepted black holes. So the question is, why are we not finding them? As I said, we kind of have to find them somehow. They should exist. So where are they? What is the problem? And there are a couple of reasons why we may or may not find them. And first of all, it can be related to this unknown black hole formation physics. We are looking for black holes in binaries. Yeah? If we have a very strong kick, maybe we disrupt a lot of the systems. So naturally, we would expect many or much less black holes than when we have no kick in our predictions. Or maybe the mass loss can also cause disruption of the binary system or a lot of different things happening. But maybe it's just our method that might not be optimized for finding black holes. Because a lot of these black holes that you saw on the earlier slide were found through spectroscopy. And also, the challenges were done through spectroscopy. So spectroscopy might just be very challenging to actually find the black holes. And this is actually true because there are a lot of things that may look like a black hole in spectroscopy, but are definitely not, and we call them black hole imposters. And so first off, maybe we just have a very low mass star compared to our massive star, so they are completely outshined by our hot blue star in the optical. Secondly, maybe we have a stripped star. Yeah, they are typically quite hot, so they are very bright in the UV, but if you're looking at optical spectroscopy, you're also going to outshine them with your massive star. And then finally, which was the cause for many of the black hole imposters recently, such as LB1 HR6819, a rapid rotator. What happens if you have a rapid rotator? Well, your spectroscopic lines, your absorption lines, are going to become very broad, and they're very easy to miss in the continuum. You can easily overlook them. And so you'll need very state-of-the-art techniques to actually look for rapid rotators. And so what the start of my PhD was about was maybe let's try to find a new method that can give us a lot of OB plus black hole systems at one go. And for this, we were going to use Gaia. What is Gaia? Well, Gaia is a space mission by the European Space Agency, and it has observed almost 2 billion stars, not only in the Milky Way, also in other galaxies, but 2 billion is unprecedentedly large. And what Gaia is most famous for is that it gives you parallaxes, or distances, and proper motions. But it gives you much more than that. It gives you the magnitude and the color of most of the stars. For low-mass stars, it even gives us radial velocities. And in 2022, we had a new data release, which was DR3. And for the first time ever, Gaia gave us astrometric binary solutions, which means that Gaia, in this catalog, for a lot of stars, it would instantly give us period and eccentricities, for example, of these binaries. So not us following up on spectroscopy, a lot of things. It was Gaia that did this for us, and it would give us these solutions. Now, how can Gaia distinguish between a single star and a binary star? If you have a single star, there are 2 contributions to your motion. You have the parallax motion, which is due to the motion of the Earth around the Sun. And since Gaia is nicely positioned in L2, it also just orbits with the Earth around the Sun. And then secondly, you have the proper motion, which is basically the motion of the star in the Milky Way. And if you combine the two, you're going to get for a single star a nice, smooth spiral motion on the sky. Now, if you add to that the motion around a companion, you're going to add this kind of wobbles, and you're going to deviate from this very nice spiral. So from the astrometry, right, which is what we do by following the motion of the star in the sky, we can distinguish between a binary and a single star, which is nice, but I want to do more. I want to not only look for binaries, I want to look for the binaries with a black hole. So how are we going to do that? And for that, it's important to realize that the binaries that we're looking at, Gaia does not resolve them. So we're not seeing the individual stars move on the sky, we're seeing the combined photocenter move on the sky. So let's take a look at this photocenter. These are two identical binaries that I show here, except that at the top we have a black hole companion, and at the bottom we have a second luminous star. If I'm going to show you now the photocenter motion, then at the top we only have one light source, so our photocenter will be located at the position of the luminous star. Whereas at the bottom we have a second light source, so the photocenter will be located somewhere in between the center of mass and the position of the most luminous star. So this photocenter motion will be much smaller than when we have a black hole. And that is the key of the method that we are going to use. We're going to look at the size of the photocenter motion. And that is exactly what's going to tell us whether we have a black hole or not. And the size of this photocenter motion is exactly what Gaia will give us with these astrometric binary solutions. So that's awesome. Now, we know what we're going to look for, but how are we going to use this information? So what are we going to use to find these black holes, these needles in a haystack of the whole Gaia catalog? And for this, we're going to use the astrometric mass ratio function, or the AMRF, because it's quite a mouthful, so I'll be using AMRF for now. And what we're going to do is we're going to theoretically look at what is the photocenter motion that a double main sequence binary can have, for example, and we're going to compare it to what do we actually see, what does Gaia give us. So let's take a look at the theoretical and the observational, and I'm going to apologize because I'm going to show you two equations, but you don't have to know the equations, of course. It's just to give you an idea of the parameters that we need. Because theoretically, it's actually quite simple to determine what the photocenter, or how much motion we expect from the photocenter, because we only need the mass ratio. In this case, we are talking about the photometric mass ratio, which means that we have the mass of the least luminous component divided by the mass of the most luminous component. And then we need the intensity ratio, or just the brightness ratio of both of the stars. So it's very simple, only two parameters. And with this, we can basically predict, or we have a measure of predicting how much a certain binary will move in the photocenter. Observationally, we need a little bit more parameters, but only four. We need the distance, or the parallax. We need the size of the photocenter motion. We need the mass, and we need the period. And if we're going to look at Gaia, Gaia will give us already three of these four parameters. Yeah? So it will give us distance, the alpha, so the photocenter motion, and then the period. And the strength in the astrometric mass ratio function is that if your observational AMRF is larger than the theoretical AMRF of any non-black hole system, you know you have a black hole. Now, to give you an idea of how it looks like, I'm going to show it to you in a diagram. So on the x-axis, we have our photometric mass ratio. On the y-axis, we have our AMRF. And so we can look at different kinds of systems. And the most easy one is, I think, the one with a black hole, because the intensity ratio is just 0, so you have a very simple, monotonically increasing function. Now, I also said that if you have a black hole next to your luminous star, this is the largest photocenter motion that you can get. So by definition, the left side of this diagram cannot be populated by any binaries. So basically what we're going to look at is here under this thick curve, under this solid curve. Now, of course, we don't only have binaries with a black hole. I think we also have double main sequence binaries. So just because of the intensity ratio and stuff, you see that it increases a bit and then goes down again. And if you have an equal mass binary of equal luminous stars, then you basically have no motion in the photocenter because it will always be located in the center of mass. So naturally, it becomes 0 at 1 and here, if you're in this regime, you actually reverse the mass ratio because your other star is more luminous. Now, we didn't only look for for binaries, we also looked at triples. It becomes a little bit more complicated, the intensity ratio, but it becomes a little bit higher. Yeah, they have a little bit a larger photocenter motion, just of how the intensity ratio between the binary and the third companion will work. Now, let's take a look at one point. Let's say I have a star, a source, with an AMRF of 0.1 and a mass ratio of 1. If I know this, I know that it is above this main sequence curve. And I told you, if my observational AMRF is larger than a theoretical AMRF, it cannot be this. So it cannot be a main sequence binary at this exact point. Now, in reality, I don't really know Q. So it might be at a mass ratio of 1.5, which would be awesome, because then it can't even be a triple, so it must be a black hole. On the other hand, it might be at a mass ratio of 0.5, and it can basically be anything. So we need to come up with a way of how to solve this without actually having to determine Q. And for this, we're going to look at the maxima of the curves. We're going to divide them in classes. Because everything that is above this maxima of this triple curve, which we call a class 3, can only be an OB plus black hole binary. Everything that is in between the maximum of this triple curve and the maximum of this main sequence curve can be a triple or a black hole binary. And everything below the maximum of the main sequence, well, it can be anything. But there's nothing to do about that. And so basically, what we're going to do is we're going to use these classes, and I'm going to look for class 3 systems, because I am basically certain that they can only be OB plus black holes. In here or in here, I'm basically going to have to do some follow-up, are they triples or not? But from this, I'm certain. Now, the theoretical curves are dependent on the intensity ratio, the brightness ratio, and this is dependent on the mass. And so this curve, this figure is just to show you that we have different curves for different masses. Now, each curve, I can still determine the classes for each curve. So just depending on the mass, I can determine whether it's a black hole or not. And so this is how we're going to find them. Now, we did some predictions, of course, because it all sounds, I hope it sounds to you as nice as it sounded for me. But so we're going to look a little bit at predictions. And so for this, we simulated a population of OB plus black hole binaries with different black hole formation scenarios. And so using Gaia and the AMRF, we determined how many we could find. And in total, 70% of our population can be retrieved with our method, with Gaia, which is quite great, because it would result in over 100 of these OB plus black hole binaries. And this would even increase the currently known sample by over a factor of 20 or so. So for the first time, we would have a real population of OB plus black hole binaries. And what is even greater, from this population, we can even try to look what is the black hole formation scenario. For example, we can look at the eccentricities. And the right plot is just a zoom in of the left plot. But so if we look at no kick, for example, we're expecting 0 eccentricities for practically all of the systems, or at least very low eccentricities. Whereas if we have a very strong kick, you can see it better here, the bulk of our eccentricity is much more shifted towards much larger values. And so just by looking at the eccentricities, which Gaia gives us instantly, we can see, or we can try to infer, do we have a strong kick or not? But we can not only look at eccentricity, we can do a similar thing with the period, for example. Now, these figures are, might seem complicated, but actually they're quite simple. So you have the period on the y-axis. The x-axis is unitless, yeah? But where it is broader, it's kind of like a probability density distribution. So where it's broader, you expect more systems in your population. It's kind of like a histogram, but then tilted, yeah? So you see that the bulk of periods is more or less at these high values for no kick. But if we have a strong kick, the bulk is shifted towards much lower values, or they're normalized. So in other words, we're actually losing a lot of the large period systems. Why is this? Because this actually makes a lot of sense. If we have larger periods and we have very strong kicks, well, these larger periods are less gravitationally bound, so it's much easier to disrupt them. And so we're basically going to lose all of the large period systems. So this is also what we can look into. Moreover, we can also look at the mass of the black hole to look at how much mass or to which kind of supernova mechanism we can have. But so by looking at these distributions, we can also tackle our problem of the unknown black hole formation physics. Now, there was this thing about black hole imposters, and the MRF diagram does not include any more depth study of the other systems. So let's take a look at how many of these not black hole systems we expect to find. So the three that I'm showing here are just the double main sequence binaries, the triples, and, well, massive stars evolve, so we have quite a lot of blue supergiants maybe as well in our catalog that we would use. Now, I simulated the population of all of these, and as it turns out, actually, we shouldn't worry about any of them. They should contribute an insignificant amount to our population. So the population that we derive should actually be largely dominated by black holes, which is very nice. So the predictions in 2022 that I made were, yay, about 100 black holes and infer the black hole formation scenario. Now, as some of you might know, I'm not going to go through all the pain of it, but we didn't find any black holes for some reasons. So hopefully with Gaia in DR4, like 2025, so probably 26, 27 or something, we can find our black holes. I'm sorry. We can find our black holes. So in the meantime, what do I do? And if I can't find them, I shall challenge the other ones. Because if I can't have my black hole, then I think the others also can't have their black hole. So for that reason, we were going to look for the system MWC656, which was the only BE plus black hole binary until last year. Now, if we're going to look at the slide I took up from all my challenged black holes, then it is actually the longest lived one. So it had a good 10 years, but I think we have to now put it aside and let the other black holes live their lives. So, right, so in the title, I don't know if you can all see it, but it has a BE-type star. What is a BE-type star? It's a special kind of massive star. Now, if you have, let's say, a normal main sequence massive star, let's say 25,000 Kelvin, this is a model spectrum, then you can see at H alpha, for example, you have a nice absorption line. This is what a normal star would give you. Now, BE stars have strong disks. So instead of a nice absorption line, you have a very chaotic emission line. That's aspect number one. Secondly, I'm going to look at another line, for example, a helium line. Yeah. If we have a relatively slowly rotating massive star, then we have very narrow lines. BE stars are very rapidly rotating, and so their lines are very broad, right? And this was what I'm telling you. This was some of the black hole imposters. This is, I think, still quite visible for hopefully most of you. But if it starts even rotating a little bit faster, you can even see that it might just completely be blended into the continuum. So very hard to compare this with normal massive stars. So our BE stars are so rapidly rotating that they are losing the matter along their equator. And this is what is forming their disk. So it's not an accretion disk, it's a decretion disk, because matter is flowing away from the star. And I show you here one example of an H alpha line in one of the BE star systems. And you can see that this emission is very variable. Sometimes you lose maybe a part of the red wing, you become broader, you become stronger, weaker. So BE stars are quite challenging. But they are very important, because a lot of recent studies suggest that BE stars are the product of binary interactions. Which means that we can nicely study close binary interactions, at least if we know the companion. Because if we know the companion, we can kind of simulate backwards, or, well, you simulate forwards, but you're going to think backwards, right? And then you can kind of try to understand what mass transfer it was and that kind of stuff. But for that, it is important to know the companion. And here is where MWC656 comes in, because it was suggested to have a black hole. Now, according to our theories, these BE plus black hole binaries should actually not exist, or at least be extremely hard to form. And so it's quite important that we find out whether this is actually a black hole, or whether our theories need some strong modifications or adaptations. Now, I'll give you a little overview of what MWC656 in the literature was already been performed. So this was done through a spectroscopic study by Casares et al. In 2014. And they used this iron 2 line. In emission, it belongs to the disk of the BE star. Yeah, they calculated radial velocities for this line. Now, very peculiar and interesting about the system is the presence of a helium-2 line, in this case in emission, but the presence of this helium-2 line indicates that you need a very hot companion. The BE star cannot be hot enough to actually show this line, to excite this line. So the mere presence of this line already indicates us, whatever we're going to determine from this line, the presence of this line tells us there is a hot companion in this system. Now, as it turns out, because of the shape and how it looks, it is actually coming from an accretion disk around a companion. So we have a hot companion with an accretion disk as well. Now, what they did is they calculated radial velocities. They got their orbital solution. So it's a binary of about 60 days with a moderate eccentricity of 0.1. And if they calculate this radial velocity semi-amplitude, you can calculate the mass ratio, and they find a mass ratio of 0.4. Now, if I know the mass of the BE star, about 10 to 16 solar mass, I can actually determine the mass of the companion, which is between 4 and 7 solar mass. And since there is no other spectral signature of a companion, it must be a dark companion, and they suggested it must be a black hole. And that was the conclusion in 2014. Now, more recently, there has been a challenge for this system. Instead of using the iron 2 line, which was an emission line, they're going to use a helium 1 line, a nice absorption line. And so what they find is that actually the mass ratio is only about half of the one previously reported. And so instead of it being a black hole, which it can now no longer be, we would end up with a hot subdwarf. Now, is this another black hole imposter? Yeah, there are two theories. But I think more importantly also is they use different lines. So is the usage of different lines actually modifying what we find as a conclusion, right? If we use emission lines or absorption lines? And so the goal of this project was to actually use new high-resolution data to actually re-evaluate the nature of the companion. And our high-resolution data is our nice Hermes data. And okay, so I'm going to show you a part of the spectrum. I'm not going to show you the spectra themselves, but I'm going to show you a dynamical spectrum. So what is that? Instead of the wavelength on the x-axis, you now have velocity space, which 0 means the central wavelength. On the y-axis, you have the phase. So I basically already ordered the spectra for you in how they occur in the period, and this is what it looks like. So every block of spectra is basically a spectra, but so they're just stacked on top of each other, and just to guide your eye even more, I show you 2 times an orbital period. And I'm going to guide your eye even more, because I think I see a very nice sinusoidal curve here. Now, this is the helium-2 line. This was what was coming from the companion, right? And I'm going to look at a line of the BE star, for example, H beta. I can already see that there is much less motion, but I can even help you with that. I don't think that is a match. So we already know that our helium-2 line is moving much more than our H beta line. We have a lot of motion in this system. So now we're going to quantify this motion, and we're going to determine the radial velocities of the spectra themselves. And for this, I use a method called cross-correlation. What do? You take a template, which is here, the orange one, and in our case, we just used one of the spectra, and we're just going to correlate it over all the spectra to calculate our radial velocities. What you get is a nice curve. It peaks at your optimal radial velocity, and by a polynomial fit, you find your radial velocity. And if we do that, first stop, what did we use for that? So I said that, well, maybe there's a difference between using emission lines and absorption lines. So part of the experience, or part of the research here, was also using different lines. And at first, we used almost all of the absorption lines available, which were helium-1 lines. You can see a couple of examples here. We used H beta, an emission line. And because it was previously used, we also used, again, the iron 2 line. Now, for the BE star, we have quite some opportunities. For the companion, we only have the helium-2 star, so we're going to have to stick with that one. And now if we calculate the radial velocities for all of these, we can show you the radial velocity curves. So here you have the helium-1 absorption line solution in the blue dots, so BE star, and then the orange stars here, the dashed line, that's for the companion, helium-2. They're very nicely in antiphase, again, nicely sinusoidal, and we find a period of, well, also almost 60 days, 0 eccentricity. But if we are looking at our radial velocity semi-amplitudes, we find a mass ratio of only 0.12, which is even less than half of what was previously reported, the 0.4, and much more in line also with the more recent study. So what does this mean for our companion mass? Well, there are a couple of measures in literature. So first off, let's see, what if we have an 8 solar mass star? That would mean that our companion is almost 1 solar mass, so we could have a white dwarf or a very hot stripped star. If we look at the 10 to 16 solar mass measure, and we're gonna look at a more extreme mass ratio within 1 sigma 0.15, then our mass is still only 2.4 solar mass. So it's a neutron star, but it's still not a black hole. Now, this 1 solar mass, this 2.4 solar mass, can it be a main sequence star? Well, I told you that helium-2 needs quite a hot object to ionize it. Well, if you look at main sequence stars of that mass, they're like maybe roughly a little bit less than 10,000 Kelvin. So it is by far not hot enough to ionize our helium-2. So it cannot be a main sequence star. So we are left with these 3 options. Now, I showed you helium-1 lines. So what about the other lines? So here you have, in this column, the helium-1 solution, second, the H beta, and the last one, iron-2. First off, let's take a look at the periods. They're all in agreement with each other, which is at least also what I would expect, even if you use absorption or emission lines. Now, if we look at the radial velocity semi-amplitudes, what we find is that they're also in agreement. So naturally, our mass ratios are also in agreement. So no matter the line we used, our results, our mass ratio, is actually robust over different spectral lines. And so our conclusion of the no black hole is actually robust over the spectral lines. So I'm sorry, but this is, again, not a black hole. Now, okay, I had my fun with this system, but of course, what do we do next? So what can we do is, maybe we can look at X-ray binaries. X-ray binaries, we know they host a compact object. Yeah, it can be a neutron star or a black hole. So this might be another way of now trying to find a couple of black holes while awaiting Gaia DR4. Now, if you don't want any spoilers, you can now close your eyes and cover your ears. But most of these systems that we are studying are not containing a black hole. Why not? Well, because practically all of them are pulsars, which basically indicates you that it is a neutron star. And this is currently ongoing work. They're still interesting systems, even though they don't host a black hole. But we're trying to calculate some radial velocities and orbital periods for them. And then I think finally for the future, I think we are all, I'm not the only one who's excited for Gaia DR4, but for now I can leave you with these conclusions.
Thank you, Soetkin, for a very interesting talk. We have time, plenty of time for discussion.
Hi, Soetkin, exciting talk. What is Gaia DR4 going to bring us that is going to enable you to find those black holes?
So it's going to bring potentially 2 things. So first off, what was new in Gaia DR3 were the astrometric binary orbits for the first time. So Gaia DR4 will bring many more, because the reason we didn't find them was because for massive stars there were no solutions. So maybe DR4 will already give us solutions, which would be convenient. But even if they don't, they're going to actually finally release the epoch data. So even if they don't produce a solution, I can fit my own astrometric solution and use this method. As hopefully they do for every star, for all the stars.
We have more questions? Yes.
Thanks for the talk. I have a question about 656 with respect to the temperature introducing helium-2 emission. Because it's an emission, that means it's in fact not the temperature of the star that counts, but it's the temperature of the accretion disk. And I think accretion disk can be hotter than the star, no? Because it's an accretion power, so I mean it's a gravitational energy changing to thermal energy. So is your assumption that it must be a hot central star because of helium-2 valid when it is an accretion disk that is emitting that?
I'm not exactly sure if you have like.
So you can have an accretion disk which is much hotter than the central object, which is the gravity. Yeah.
Yeah, but so what would be the temperature of an accretion disk of, like, for example, let's say pre-main sequence stars or something that are accreting? Is it like temperatures to excite helium-2?
Yes, I think so. But I have to compute. I don't know. I have to compute it. But I mean, I think that an accretion disk temperature can be much hotter than the central star. And we have, I have to compute what is the potential energy changing to thermal energy, but
Oh, yeah.
yeah, but depends on the accretion.
I cannot give you an answer. Maybe we can like.
But
look
I mean, the
into it or
temperature of
check
the
it,
accretion
but,
disk is important, not the temperature of the central star. This is in fact my message.
Yeah.
Or question.
Maybe to pick up on this, it seems that the fact that your line is in emission is the key here. Would an ASDO star produce a line in emission?
In the disk, yes.
Well, in the
So-
disk, yes. But
And if it has, if it would have strong winds. So, for example, if you would have a very powerful wind, but the thing is, the shape of the line can tell you a little bit. So it is quite nicely double-peaked, which kind of indicates that it comes from a disk. Whereas a wind would not give you a nice, like an. Oh. So it's like hard to see. In some structures, better to see, but there's kind of like, this is not the shape you expect for a wind, for example. So this tells you that it would be coming from a disk.
yeah, so basically your conclusions apply to the disk, not to the
Yes.
center of object. Okay. You have more questions? Yeah.
Really nice talk. You said that for low mass stars, you can get radial velocities. What are the prospects for doing this for massive stars? Is that on the horizon, or is that fundamentally limited?
So, well, as right now, Gaia calculates or gives you the radial velocities based on the calcium triplet around the 8,000, in the 8,000 region, which massive stars do not show. So they have the Paschen series there, right? But so Gaia does not do that. If they release the spectra, maybe, I don't know how wide the range is exactly, but I wouldn't like bet my money on it.
Hey, thanks for the nice talk. Out of curiosity, do you think the other Gaia quality flags could be useful for such a study, the astrometric noise or the Rouvet and these things?
There are some groups or there is some literature on that. I don't remember exactly what parameter it was, but it had to do indeed with the excess noise compared to the solution. I have to say I did not look into that, but there is definitely people that, well, I don't know if everyone actually looked into that, but there are definitely people who suggested to look into that. I don't know how easy it would, because there is, I mean, the excess noise, yeah, I don't know, there is a lot of things going on sometimes in the systems, right? So I don't know if it would be solely attributed to, but you could maybe select some systems and then kind of...
the flagging or...
Yeah, something like that, yeah.
Given the mic is here. Quick question. So I remember more or less we were in Leiden talking with Casares, and I think wasn't there this issue that they were measuring different RVs for the iron line, and there was this discrepancy. So
Yes, so
was that ever figured out?
No. So what they have, so the big problem is that their RV semi-amplitude of the iron 2 line is basically almost double of what we find, and I could speculate on possible reasons why that would be, but we never actually sell this, because we had indeed a chat, right, together, where we said, like, look, we find only half, and also these Rivinius also found only half, basically in agreement with what we have. On the same data as well, yes, with a lot of methods that we tried. We didn't only try cross-correlation, we even tried to reproduce their method. We did not find their radial velocities. We didn't settle this. We don't know.
Yeah, I guess it's 2 versus 1 at least, because two
It's
people
2 versus
tried.
1 plus we also, well, yeah. So we did it on their data and on new data. So yeah.
Okay.
We have more questions? Pierre, you want to ask a question?
No, a quick one. I see that you still have 4 surviving. In your cleaning, you still have 4 surviving. Are those your next?
No, that's true. There are still a couple of survivors. I also don't. I mean, Gaia did some great stuff, by the way. I don't want to like. There are like two Gaia black holes, okay? Just, but only around low mass stars, which are probably the only 2 that were in there. But.
In the intro, you said that you would expect like 10 black hole binaries within 3 parsecs.
Yeah, 10. I meant a little bit order.
Yeah, but
of a couple of things,
how
yes.
many OB stars are there within 3 parsecs?
Oh, right, did I
because it
write
said
parsecs? Oops, sorry. Kiloparsec. Kiloparsec. Well, but
Thank
then
you.
even you could extrapolate it, right? If it would be within parsec, you would
Yeah.
expect like...
Quite a lot.
No, sorry, I meant kiloparsec.
Okay, thank you.
More questions? Ooh.
Thanks for a very nice talk, Soetkin. Can you go to your slide 18, please? To your AMRF versus Q diagram.
Okay, which
yeah,
this one or... Yeah,
This
I have
will
several, so
do.
just... yeah.
So here you show, So here you show the different curves for binaries and triples. But what happens if you have a more complex system? Let's say a multiple system of 7 stars.
Yes. So we did the experiment, and let's first go only 1 step further, and let's look at a quadruple system. So what you can do is you can look at the extremes of, for example, a quadruple system. Either you have, let's say, well, I don't know exactly maybe by heart, again, how it went, but if you have like an equal mass, well, okay, no. Most extreme scenario, you have, like, let's say, hierarchical triple, you have 2 binaries, and you have one with, like, an extremely massive star and, like, an extremely low mass ratio, so you have basically negligible, and then in the other case, the same thing. Then you're gonna end up at the main sequence curve, at the double main sequence curve. Binary curve. The binary curve. Now, you can also go the other way, so if you would have, like, one of these systems where you have the extreme mass ratio, and the other one you have an equal mass, you're gonna more or less relate to the triple curve. And you can actually look at all the in-betweens. We did the experiment as well. So what is actually happening is that all the more complicated systems, you can in the end somehow lower them back to, for example, the triple system. And actually, the triple system is like the worst case you can have. Because even like the quintuple system, you can again like lower it into the quarter and then move it backwards. And so basically, what we expect, right, is that all these systems, like if you would have a 9 solar mass luminous star that you would see, then basically whatever configuration it is in, it will be below the curves.
Okay. Thanks.
I had the exact same question.
More questions?
Also on this diagram, you said that like everything to the lower right of the black curve, you would have like black holes in there on the top right, right?
Yeah. So let's say I have a 30 solar mass star. If it is anywhere located above this line in the, well, it can't be located here anyway. So if it's anywhere located here, it should have a dark companion.
Exactly. So the companion is dark. How do you get like to the right of this black curve? So you said that if you're a main sequence star and a black hole, then it's on the black curve, right?
Yeah. You mean how do you get?
How do you get below?
So
right?
This has to do with orientation. So if you have a perfectly circular system, no matter how you look at it, it will fall exactly on the curve. Now, if you add up a little bit of eccentricity, depending on how you look at it, your photometric mass rate, your photocenter motion will become smaller and smaller, and so you're basically going to shift downwards in the diagram.
Okay, thank you.
More? I'll have a naive general question myself. So basically, so to what extent everything that you have presented, yeah, including the the evolutionary path of the binaries, can be extrapolated to neutron star companions?
Practically everything, I think.
Because we also, we observe main sequence plus main sequence binaries. We also observe the double neutron star through gravitational waves, weaker signal. Are there many main sequence plus neutron star binaries observed? If not, what does the theory say about it, if you know?
Well, I know most of. So the thing is, it becomes, of course, even more difficult to find even a lower mass dark companion next to a very massive star. But most of the X-ray binaries are actually neutron stars. So at least we know that there are a lot of X-ray binaries that host neutron stars. So naturally, the step before should also exist. But it's even more difficult to find them. They should be more abundant, I think, because neutron stars should be a little bit more abundant. But I was just about to say that. Sorry.
Who is that guy in the audience?
So indeed, what Uke is saying is right. So the thing is, if you have a neutron star, so even with this method, your neutron stars might, let's say, they're going to hide somewhere here or so in this region, but so they're never going to be able to pop up over our class tree. And so even with this method, you would not, this would work much better for black holes. Of course, if you have a much lower mass star, you're of course gonna, if you have a neutron star, gonna go much more over here. Well, the curves are gonna go up as well, but it becomes a little bit more easy to find neutron stars. But yeah, around massive stars.
And maybe one more question from me as well. You see my questions are questions of an amateur here, basically. So you talk a lot about Gaia, yeah? But you mentioned X-ray binaries as well. So you do expect some black holes to be X-ray binaries, right? So black hole companions. Have you thought, or maybe looked even, into the Rosetta data? So the mission that is going after the X-ray sources, supposedly full sky, but because of some political situation in this world, it's only half sky that is released to the European community.
No, I haven't looked into that yet. Okay.
Yeah, might be an interesting maybe mission for you to look at. Okay. I think they are having or maybe they are having a data release today, I believe. The Astrometric page should be flooded with Rosetta papers today. More questions? Oh, a lot. That's good.
So at one point you showed this nice spectra of a fast rotator, and it was like this very shallow and it was hard to see. But how I understand rotation is that the equivalent width shouldn't really change. It just goes from a small peak and it just widens out. But in your plots it showed like there was basically nothing there. Is that like a normalization thing that just becomes very hard to normalize it? Or is it really just that it becomes so shallow? Because it looks like I'm losing equivalent width somehow. Or maybe I'm just not seeing it correctly. Like in the other lines as well, I'm just losing them completely.
Yeah, so okay, I'm also, honestly, I don't know if this was the correct model. It was just for illustration purposes, but you might in general be right that it anyway may seem like much shallower or like much, but it becomes very difficult. I think you can really lose parts in the wings that you kind of like, maybe you normalize them out, but even not, the difference becomes like so small that you can't see them. So the lines these ones, for example, are just completely blended out in the noise. So if in an ideal world I would have maybe my perfect zero noise spectrum, I might be able to see like a little bit of that, but it's...
Okay, yeah, sure. Makes sense.
In the case of your MWC target, it clearly has an accretion disk, right, the companion? So I was wondering if you expect accretion disks around your compact companions, will that change your plots of the photocenter displacement, where you have the different classes? Because I suspect there will be some brightness in the due to the accretion disk itself.
You mean in the ones I was initially looking for?
Yep.
Or yeah. So the thing there is that the accretion disk, if it would change the brightness, I think, yeah, well, it will depend on the temperature probably, but it might increase a little bit, or decrease a little bit the photocenter motion. That's true. But in general, the ones we are expecting to find more are pre-interaction. Well, or pre-interaction with the black hole at least, or the compact object. So we shouldn't really expect an accretion disk around them yet.
Yeah, so you don't expect that to affect, for example, your around 100 black hole estimate for the Gaia sample?
I don't think that will be the major factor impacting that number.
Okay,
I'll,
thanks.
put it in these words.
More questions? No? Soetkin, are you looking into some all-sky ground-based spectroscopic service? I understand spectroscopy is not the best method for you, as I got from your talk, but maybe just looking for candidates?
This is what Laurent Mahy and the team did at least with the SD9. SD9 is a program with that one. What?
SD9 binary
SB9,
catalog.
SB9, yes,
SB9.
not SD9, SB9. And so he looked at the single-line spectroscopic binaries and trying to find, and one more or less confirmed candidate came out of that. But I'm not currently doing any more. Yeah. Yeah, you also need quite high, good resolution, low signal to noise, to actually be able to distinguish between non-black holes and.
Yeah. So for the recording, the comment in the audience is that most of the archival data do not have enough quality, but so the all-sky spectroscopic surveys, like LAMOST, SDS, LAMOST is not all-sky but northern hemisphere, but those are low resolution, so higher signal to noise, and I believe low resolution is okay for these rapidly rotating stars. Maybe looking into those.
Depends on the resolution you're talking about, right? You need 5 or 6,000. The 2,000 doesn't cut it. There is a real difference between 5 and 6,000 and 2,000. Maybe it can be used to screen some candidates and then to follow up at higher resolution. You don't need 40,000 because some of them are fast rotators, so that doesn't matter. But there is a big difference between 2,000 and 4,000. The other thing is things like LAMOS, for example, signal to noise is scrapped, normalization is scrapped, data reduction is scrapped. So that is useless. It's clear. SDSS is much better, as you know. So there maybe there will be work to be done there.
Yeah, the advantage of low res is, of course, these guys probe much deeper, so you can expect more candidates just by volume, I guess, right? Yeah. Okay, we are almost at the hour, so thanks, Soetkin, for the nice talk, and thanks, everyone, for the discussion. See you next week.